Hi Algebra 1 students, this video is on quadratic functions. It's based off of Module 4, Lesson 8 in your Eureka workbooks. And I'm just going to kind of do a quick overview of what this unit is going to be kind of focused on, as well as what is some of our vocabulary words. So notice along the top of this worksheet, you see the words quadratic expressions, quadratic equations, and quadratic functions. So we have actually already looked at quadratic expressions and quadratic equations, and now what we're moving into is quadratic functions. So quadratic expressions we'll see of this form. We call this the standard form of a quadratic expression, where you have ax squared plus bx plus c. This is an expression because there is no equal sign. It is not an equation. And then an example, write in a different color, would be something like x squared minus 6x plus 5. And primarily what we were doing with something like that would be to say, can we factor this, right? That's what we were doing with quadratic expressions before. Then we looked at quadratic equations, where we still had the ax squared plus bx plus c, but then we had an equal sign. And the standard form of a quadratic equation is where you set that equal to 0. And in this case, when we were looking at quadratic equations, it might look something like 0 equals x squared minus 6x plus 5. Where this is a quadratic equation, we could factor, use the zero product property, and then solve for x, right? So it's related to this quadratic expression, but it's a little bit different because now we have equal to a number equal to 0. Now we're going to get into quadratic functions. So functions have an input and an output. So instead of having the equal to 0, we're going to have f of x equals, and then the standard form ax squared plus bx plus c. So what it looks like as an example would be f of x equals x squared minus 6x plus 5. And we could plug in values for x and then get an output for y and plot the points. And that should create the graph of a quadratic function. So graphically, what we were exploring in class today was that we get this U shape when we plot the points we get with input and output values from a quadratic function. And a couple of vocabulary words about this. I just want to kind of add one in here, which is that we call this entire shape a parabola. So off over here, I'm going to actually define some of these words for us. So we say a parabola. That is the word we use to describe the graph of a quadratic function. So that says quadratic. I know it's a little bit hard to read. Function. So parabola is the graph of a quadratic function. You can also think of it as the U-shape curve. The next thing I want to talk about is the axis of symmetry. We looked at the axis of symmetry in class today when we were thinking about points on either side being symmetrical. So the axis of symmetry is, I'm going to highlight it, it's this line right here that goes through the vertex, and it divides our parabola into two equal halves. So if we can imagine, if we were to fold our piece of paper along this line, the left-hand side would match perfectly to the right-hand side. So in terms of a definition, we say the axis of symmetry is a line that divides the parabola into two mirror images. And given a quadratic equation in standard form, there is actually a formula that gives us the axis of symmetry, which will always be negative b over 2a if you have a quadratic function like ax squared plus bx plus c. Okay? And I'm just going to kind of denote that on our picture as well. So to kind of highlight, we have the axis of symmetry is that vertical line that splits it in half. And I'm just going to denote x equals negative b over 2a will give you that x value. Because a vertical line, remember, is always just x equals a number. So it's going to tell you what number. In this case, it would be 1, right? Okay, one more definition for you guys, and that is for the vertex. The vertex is the point. So like generally it's this like center point on our graph, but we have kind of a more formal definition, which is the point where the graph and the axis of symmetry intersect. So if you notice, we have our axis of symmetry and it is splitting the graph straight in half, so there's one point at which it's going to cross our graph, and that is at the vertex. Now, the other thing to note about the vertex is that it will always be either a maximum or a minimum. And I'm just going to kind of, again, denote that on here. So we're going to say max or min to kind of remind ourselves. And then the other things that are labeled on here are things you're pretty familiar with. We have the y-intercept, which is where does the parabola cross the y-axis. And the way we're going to, there's actually a way to see that in the equation, which is that the y-intercept is where x is 0, right? So if you think about it, it will always be, have an x, the coordinate, if I were to write an ordered pair, the x value would be 0. The y value, if you imagine plugging in 0 for x into the standard form, well, you'd have the ax squared term would be 0, the bx term would be 0, and you'd be left with just c as your y value or your output. So the y-intercept will always be that c value, or 0 comma c. And then the last thing on here are x-intercepts. The x-intercepts are where y is 0, right? So it's these 2 points right here. It's where you're crossing the x-axis. And just note that if it's where y is 0, it's the solution to the equation where we plug in 0 for the f of x value. So like everything we've been doing with factoring might actually help us to find y-intercepts of a graph. Okay, so that is the basic overview of some of the big vocabulary words. The last thing we're going to talk about is end behavior. End behavior is something we'll be dealing with more formally in Algebra 2, but for our purposes in Algebra 1, you can think about end behavior as what's going on at the ends of the graph. What's going on at the ends, and that's kind of like a, I'm putting this in quotes because we want to think about what we mean by ends, at the ends of the graph. And the idea is the ends are like as the arrows continue. So if you have, I'm just going to quickly draw a little picture here. We have some quadratic. The end behavior is looking at what's going on after those two arrows. Well, in this case, they keep going up, right? So that's something we're going to be thinking about when we think about end behavior. And we have these sort of two outcomes when we are thinking about what's going on with the arrows. Either they're facing up or they're facing down, right? So we call, if the arrows are pointing up, we call that opens up. If the arrows are pointing down, we call that opens down. We're going to quickly, I'm going to draw a little graph for each, and we're going to denote some important characteristics of both. So for opens up, I'm going to sketch in a parabola that is facing up. I'm going to say its vertex is about there. I'm going to sketch in the axis of symmetry. And I'm going to do the same thing over here. So I'm going to draw a parabola that's opening down now. I'm going to say the vertex is right there. Draw in the axis of symmetry. Okay, so we get these two types of end behaviors. And it has to do with the a value of the standard form function. So remember, a is the leading coefficient. It's the number in front of x squared. So on here, the idea is if a is greater than 0, that means it's positive. Then we will always see that the graph is opening up. If a is less than 0 or negative, that's when your graph is going to get reflected over and be facing down. The only last kind of big idea here is that if it's opening up, that vertex will be a minimum, right? And if it's opening down, the vertex will be a maximum. So in opening up, we're going to have the minimum value will occur at the vertex. And if it's opening down, we'll have a maximum value at the vertex. The last thing I'm going to put on these two little graphs is to think about where is it increasing and where is it decreasing. So if we kind of think from left to right along this first graph, to start, if we imagine walking along, is it increasing or decreasing? Are you going uphill or downhill? You're going downhill. So this part would be decreasing. And then at the vertex, it switches over and starts to go up. And here in the opening up down version, it's going to be the opposite, right? When we start off, we're going up, and then in the second half after the vertex, we're going down. I spelled decreasing wrong, but I'm going to try to fix it. And the last thing I want to address here is that how do we deal with the notation of describing a decreasing or an increasing interval? And so the idea is, like, suppose I'm going to just give this vertex, I'm going to say it's the point HK. H and K are letters we typically use to describe the vertex, but we can imagine H and K are specific numbers on this graph. And same for this one, if we call this the point H comma K as our vertex. Then we would say this graph is decreasing for x values less than my vertex x value, right? So everything to the left would be x values less than the x value of H. So supposing this is actually a specific value, you would say we know our function is decreasing when x is less than H, where H is the x value of the vertex, and then it's increasing when x is greater than H, where H is the x value of the vertex. We're going to get something similar over here, except where we're increasing when x is less than H, and we're decreasing when x is greater than H. And that's just to give you some idea of, like, how will you describe the interval of increasing or decreasing. And that's all that I have for these notes. You are also completing the problem set in lesson 8, 1 through 4, and we will be moving on with looking at different types of quadratic graphs tomorrow in class.